Hello friends, very good morning. Last lecture, the last chapter, that is a serial communication. In that, the SPI communication we have done with that, that is called a serial peripheral communication, and various modes of operation of that based on the phase and the clock, how it is given. Okay, so basically, if we talk about just, I have the revision of that serial peripheral interface that can be formed using the 4 wires. Okay, and that 4 wires are mentioned here as a clock, serial clock, master out, slave in, master in, slave out, and SS, slave select. So this is our actually controller. All these other are the peripheral devices need to be connected to, along with the controller. So when this controller want to send the data to the other peripheral, and after each serial clock pulse, data is going to be shifting out serially. Okay, and that data goes from the master out pin, the slave in. Okay, so from that, and this pin is connected to the master out of the pin of the slave device. So means if you want to send the data to the first slave from the master, it is going to be sent like this. Otherwise, other slaves, or can say peripheral, need to send the data from that to the controller. It goes from always the line master in, slave out. Okay, and by enabling appropriate slave select device, this controller will send, if you want to send the data to the slave 2, the SS bar signal pin of that, it is going to be enabled from the controller, and they perform the communication between the master and the slave. This is simple working. It can have the one slave, one master, many slaves, a number of slaves, and one master. That way the communication. The next peripheral we have communication protocol that is called as a I2C bus. That is called as a inter-integrated circuit bus or two-wire interface. Sometimes it is called as a two-wire interface. Okay, if we talk about a drawback with the SPI communication, when the data is sent from that controller to the slaves, there is no communication between that slave and the master after the data is received or not. Means no acknowledgement will be there. But because of that, controller never understand that my data is transmitted or not. Okay, so after some time interval, you need to send the retransmit the data, send data. This drawback is overcome in case of the I2C communication bus, that is called as the inter-integrated circuit bus. Only two wires are there. One is called as a data wire SDA line, other is called as SCL line. So serial data line and another called as a serial clock line. Okay, so using these two wires, the I2C communication will be takes place. So why the name given inter-integrated? When there is having a large number of ICs and one have the very large board, you can say the our monitors, computer monitors, LCD TVs, LED TVs, mobile phones. We can see that in the small PCB we have to connect number of SMD format devices or the ICs. Then when master controller always will be there, processor will be there, and needs to communicate with the other peripherals like IO ports and keyboards and all these things, or LCD. So such case will be there. That time I need to connect the bus between the one master and another, all the peripherals. So that forms or connection. So depends upon the size of I2C bus, how many devices can be connected, can be configured. Okay, so if I have the 8-bit serial bus, so based on the 8-bit serial bus, I can connect the, if the size is going to be 8-bit only, okay, then 2 raised to 8, that is going to be 256 devices can be connected. Okay, if the 7-bit serial bus, I2C bus, 2 raised to 7 means it is a 128 devices can be connected. For the 10-bit, 2 raised to 10, that is going to be 1024. So how many devices can be connected always depends upon the size of the bus. It will be 7-bit, 8-bit, and the 10-bit maximum they are using I2C bus connection. So how to select? As I mentioned that. So how many devices need to be connected to the controller, and we can purchase based on the size of the I2C bus. If it is 7-bit, I can connect 128 devices. 10-bit, 1024 devices. So 1024 is sufficient. We can interface that number of devices. Okay. So how it performs the communication, we have to send some conditions, signals on this serial clock. Then the data will be transferred to the particular device by with the help of the address. And in this case, the address of each slave need to be taken in while we do the programming of the device. Means simply to which device control need to send the data that can be transferred by using the address of that. We'll see that part also. So here one master and multiple slaves can be connected. So how the connection will be taken here, as I mentioned, it is discussed. So this is the diagram. So I can take this or this, both are the diagrams are correct. See here. So we have the one master controller, and that I can say this is a peak. So in the peak we have the I2C bus also, or Arduino board also. Okay, so from this device, I can transmit the data over the SDA line. Okay, so on this SDA line, I have the data, and on the serial clock, based on the clock signal, it is going from high to low or low to high. The conditions of that working of I2C is mentioned. Okay, this will be slave 1, this will be slave 2, like this, we have the n number of slaves. If this is 8-bit bus, I2C bus, then I have to connect the 256 devices, means 0 to 255 devices can be connected. And for each device, I am assigning one unique address. That is going to be 8-bit address. Like this, I have the 0xFF. So this address need to be considered while we programming. Means if the controller want to send the data to the slave 1, so the slave 1 has the address 0x01. So to this address only it will send the data. Okay. So once the data is sent by generating clock high to low or low to high, so after that the slave device also send the acknowledgement signal to the controller. So by saying that I have received the data. If after some time interval again, if acknowledgement not considered received by the controller, he retransmit the data to the that slave device. Okay, so this is not in the SPI communication. So this thing is overcome in the I2C bus. Okay, means there is a proper communication between the master and the other slaves by using the I2C bus or two-wire cable, also interface cable. Means control send the data, at the same time it can get the acknowledgement I have received the data. So we can say it is a simple proper communication, means the data is not only getting the intimation of that. Simple technique like if we see our postal, when we do the speed post and we're getting one acknowledgement number and we're tracking that. Same way, once data is received, the slaves transmit or give the acknowledgement signal to the master. I have received the data. So what are the devices to be connected? As I mentioned in the second diagram, this is my master and the slave 1, 2, 3, 4, like this n number of slaves can be connected, these two wires. And what are devices? I can connect controller along with the sensors. Various sensors can be interfaced here. There will be ultrasonic temperature sensors, motion sensor, PI sensor, anything. RTC model I can say, or the clock, or real-time clock, or the clock signal or watch I can connect to the this controller through the I2C bus also. Then different memories, ROM, RAM memories need to be external interface that can be connected. Then displays, LCD displays, LED displays, bar displays, or different displays can be connected here. Keyboard is there. It may be motor may be there. Any device can be connected by using this I2C bus to the controller. Okay, so this why it is needed, as I said that if we talk about any controller, we have the limited port pins are there. Okay, so because of that, I cannot go with the maximum interfacing of that. But by using that serial communication protocol, that is, I have the I2C or SPI communication, to which I can connect the n number of devices like this parallel here. So based on the application, in just I mentioned all the television receivers, set-top box, monitors, LCDs, where we need more ICs to be connected along with the controller. I am using the I2C bus, and the speed of operation also can be decided. Maximum speed can be provided based on the it's a classification of the I2C bus will be there. Okay. So this is a simple operation of I to C bus when I connect the multiple devices along with the controller. Let's go with the next diagram. Okay, say see same diagram is shown here. Uh, Two wires are required, but by default we have the VCC ground, and that must be there for all kind of serial protocol models. Same here is mentioned. I using the Arduino master here is shown here, and VCC and ground supply is taken from the pins and can be given. And what are the other devices? Slave 1, slave 2 can be connected here. It is shown here. It is LCD, and it is one of the I can say it may be the not exactly getting. It may be the one Wi-Fi model or something SCL, SCM getting there, or any other protocol model can be connected here. This is simple diagram to shown how the devices can be connected to the I2C bus. So it can have the multi-master also. As I said that one master is not there, it can have the multi-master also. So multiple controllers can be connected among between the slaves. And address of that can be defined. And it has the fixed format for the communication, that is called as a frame format. That will be seen the last part, will be there in that last part. So theory operation is mentioned here. Once we are connecting the I2C bus, that is SDSL cable to the other slaves, what is required? The master will always initiate the communication between the slave devices. So master will send the address of target slave. As I mentioned that 0102 means if it is 8 bit, 2 raised to 8, that is 25502. That number of devices can be interface, and always address of that slave will be sent from the master. Then based on that read write flag will be communication will takes place. The slave device with the matching address response acknowledgement means which address assigned at which pin it is connected, address number 2. So means that slave number 2 will give the acknowledgement, as I said, that toward the controller. So I have received your address, and between them slave that 2 and the master starts the communication. Okay, so both master and slave can receive or transmit data depending upon the communication, either it is reading or writing. So it is a simple half duplex. It's not full duplex, means only a control will be sent or slave will be sent, means at a one time only. So frame format we talk 8-bit data can be transmitted along with the 1 bit of acknowledgement. Okay, so the same diagram we discussed just now, multi-master communication. So this is the frame format, how the frame format will be there. Either I can have the address as mentioned, the size of the I2C bus 7 or the 10 bits. That number of address will be there. So I'm mentioning here address to which I'm sending the data. Means first in initiating the start condition, then I have the address of 01020. How many maybe maximum? 255. It is a 8 bit. 10 bit 1024. That number of addresses. It is 10 bit address. Okay. So address frame will be mentioned here. I'm sending the data to which particular device. Then based on the condition, read bar or the write, means if it is a read signal is there, it will be 1. If it is write bar means it is 0. So I'm reading means what? I'm receiving the data from the slave. Write means if it is 0, this bit will be 0. I'm sending the data from master to the slave. So this bit will be defined. Okay. So here is the mention of what signal will be acknowledged. I'm sending data and the register node from the slave device. After this initial some bits, I have exactly what data need to be sent from control to the other slave. That is called as a 8-bit data. And once this data is will be received, the acknowledged signal from the slave will be comes back and received from the controller. Like this, next 8-bit data, then acknowledgement. Then if you want to stop the communication, use the stop condition. Now, what is the start and stop condition? It is shown here. Let's understand here. So what is start condition? SDS signal goes from high to low. At the same time, SL is going to be no change, constant. Means high, we can say it is high to low. Start condition is mentioned here. High to low transition on the SDA line. When SL is high, that is meaning of start condition. So when the start condition will be made, I must send the clock SDA line must be low to high. Sorry, high to low signal. And the clock at the same time clock will must be high level. And during the data transmission, the signal is mentioned, both signal must be high. Okay, during the data transmission. And for if the data is over between the communication, that is called the SDA goes from low to high, the same time clock will be high. So when the signal is coming like this, low to high on SDA line and the clock will be high, I can say that the data communication will be stopped between that slave device and the controller. So this diagram also is important to understand to make how device will be start and the stop data transmission between the slave and the master controller. Okay, so again I'm repeating the MCQ is asking on this. SDA line high to low signal clock will be high. That is the start condition on the I to C bus. The same time stop condition reverse way, low to high signal on the SDA line and clock also be high only. In the both case clock is high, signal high to low, start condition, low to high, stop condition. And to become the data, both signal must be high level. That is forms the data transmission. So these some terminologies mentioned here. What is address frame, stop condition? Just we discuss in that frame format. They have explained here only. Okay. Based on the MCQ, also is asking what is the size of address and how many bits address will be defined, if it is 10 bit or 7 bit or 8 bit I2C bus. These are the features. As I said that what is the data rate transmitted over the this SDA line or the on SDA line, serial data line. So based on that, it had a classification. It supports for multiple speeds from 100 kbps in the standard operating mode of I2C bus. The fast will be there 400 kbps and industrial 3.4 high speed 3.4 mbps. Okay, so this is MCQ is asking on this. What is the speed for the standard I2C bus? It is 100 kbps. If it is in the fast mode operation, 400 kbps, and for high speed 3.4 mbps. And size is going to be always 10 bit addressing. Okay, and the things as mentioned here, ultra also it is there, ultra high speed for the 5 mbps. And by default I2C is a serial communication will be there. It is a synchronous because I'm using the clock signal. Okay, how many masters will be there? Unlimited. How many slaves? If it is a 10 bit, 1024 devices can be connected. That is mentioned here. This is some features of the I2C bus. So it is advantages mentioned. I'll go with the some difference between I2C and SPI communication. I2C requires only 2 wires. It requires the 4 wires, as you know that. Low speed, it is high speed communication SPI. Half duplex means only one transmitter at a time, but SPI is a full duplex because we have the 2 separate lines. That is master out, slave in, and slave out, master in. So by different 2 wires can perform the full duplex communication. So additional signal select line not required in case of slave device because we have the addresses to send the data between the slave and the master. But in case of SPI, SS bar signal is used to perform the communication between the by selecting the slave lines, sending the signal on that from the controller. That is the additional signal that is called SS slave select line. More power required here in case of I2C, but in case of SPI low power is required. So the multi-master can be easily used. Multi-master is quite a little bit difficult in case of SPI communication. So this is a simple difference between I2C and SPI. One more we can add that. So one signal is transmitted, I can have the acknowledgement signal can be generated. Signal given. Signal given from transmitter and between transmitter and receiver. Transmitter and receiver. But in case of no acknowledgement signal in SPI, this will be additional 1 point. Then this is again shown here what is SPI and how devices connected. Okay, slave select lines are there for selection. 4 slaves are there. 4 lines will be there. These things are repeated. No issue in that. So SPI is developed and try to understand it is a Motorola and I2C is by NXP. Okay, the last serial communication protocol in this chapter, that is serial communication, that is called as a USART. Okay, so meaning of USART is what? Universal synchronous or synchronous receiver transmitter. U is for universal, S is for synchronous, A is for asynchronous, RT receiver transmitter. This is full form of that. So the USART is available in the peak controller, and how the communication will be takes place by using USART port. Two pins will be there for that, and some registers will be for the controlling and finding how the bits can be assigned. It is mentioned here. Let's understand that bit format of the control registers of the USART, that is mentioned by TXSTA, that is transmit status control registers. Okay, so it is 8-bit registers starting with the address. We can see bit number 7, CSRC. That is called a clock row select bit. Means what is the clock signal or applied that can be configured from this pin. So it is operating either in the asynchronous, synchronous. By finding this either clock is applied or not, I can understand from the this bit. Okay, then I have the TX9 bit. When this bit will be set when there will be 9-bit data transmission will be takes place. The means 8-bit will be data and the 1-bit extra that will indicate here. That is the 9-bit for the extra bit for the data transmission or communication. TX enable. Setting this bit enables it starts the transmission. When this bit will be high, means from the user the data will be transmitted in the synchronous mode. Okay, that is meaning of the this. If the 0 will be there, no communication, no transmission between them. It may be in the receiver case. Then I have the sync bit. The sync bit is called as synchronization. Either I can define asynchronous, the synchronous. It may be here only. Same day. User define which mode is operating. It is 1 synchronous mode and 0 asynchronous mode. Then we have the next bit is going to be bit 3 is not used to keep a future. BRGH, high baud rate select bit. So when we want to multiple baud rates like 9600, 12400 or 2400, so that bit baud rate can be increased by setting the high level bit on this bit. Means when this bit will be high, it operates in the high baud rate communication, in the 0 low baud rate communication. Then TRMT, transmit chip registers, is there. That is called a serial buffer register also. So if you see the control also serial communication, internally we have the SBUF. Similarly, it has the TSR, transmit serial register, and the receive RSR, receive serial registers. So when the data will be transmitted, the data always stores in the this TSR or the RSR. In case of the reception, it in the ISR, RSR. Okay. So indication that bit, if the TRMT bit is 1, that indicates the it is empty. No data is received in this bit. So on this bit it is 1, no data is received here or transmission it is not there. It is empty. Okay. If the 0, it is full. Simply it indicates that like token. If this bit is 1 holding 1, it is empty. If this token is acquired other, it will be full. Means data is stored in that case. And last bit is called the TX9D. This is 9th data bit for the 9-bit communication mode. If you see here, we have seen if this bit is 1, that means what we are performing the communication as a 9-bit data. 8-bit here and the 1 extra bit will come and the at bit number 0. This is simple transmit control register and how it is perform the communication, either asynchronous, synchronous, high baud rate, mode baud rate. It is mentioned in the this SFR, that is special function control registers of the peak controller. Then similarly, we have the receive status in the control register, that is RCS STA. Similar way as we discussed previous, that is the transmit control register, we have the receive control registers. Same way it is a 8-bit format, and along with 8-bit also I can perform the 9th bit for the reception by indicating the bit number 0. RX9D indicates the reception of the 1 extra bit, that is 9. It is located in the this bit position. And if the 9th bit will be data received, when at the bit number 6 it will be high. RX9. This indicates we have the communication of the 9 bit. Okay, starting with the first bit, SPAN, that is called as to perform the serial communication of this data, that will enable the port of that. That is serial port enable bit. Okay, so writing 1 on this bit number 7, it will be enable the serial port for the reception. If it is 0, it will be disabled. Means the data will not be received by that USART port. That just mentioned RX9. I can perform the 9-bit transmission by writing 1. 0 means it's simple 8-bit communication. Then we have the next bit number 5, that is SREN, single receive enable bit. Means writing 1 on this will be performing the reception of the data inside the USART. Means if you want to receive the data one time or a multiple time, that can be configured. Only one time, this indicates the writing 1. Only one time data will be received. If CREN, continuous receive, will be enabled, the multiple data will be received by the USART port. That is writing 1. That is CREN, continuous receive enable bit. Then we have ADEN, address detectable enable bit. So this address will be used for what? This bit is applicable only in the asynchronous bit when the 9th bit is a address. That when we perform the asynchronous communication from the transmitter side, if you see here, if we want to use it is 0, it is asynchronous, and using the 9th bit communication, that time the address of that will be indicated in the add-in, that is address detect enable bit. Okay, then we have FERR, the framing error bit. 1 indicates framing error occurs, 0 means no framing error. Means what is the frame format we are selecting? In that certain bit level error is occurred or not, this is indicated by this bit. Okay. The next is OERR, overrun error bit. Means data is going to be greater than 8-bit, 9-bit. That is indicated in the bit number 2. That is means overrun. Data is high level or low level. Means greater than the 8-bit or the 9-bit. And the bit number 0 as mentioned, this will be always 9th bit as a data reception when this bit will be high. Let's see how USART operates. So USART has the baud rate generator, that is called BRG. With the chain in the transmitter, we have the BRGH. To define the baud rate, it is high or low by sending on the 1 or 0. 1 means high baud rate, 0 means low baud rate. So this baud rate can be configured high or low by using the baud rate generated BRG. Okay, and how to find this BRG baud rate in the synchronous or asynchronous mode? It is mentioned in the formula. F the frequency, crystal clear frequency weight, what is they connecting? That frequency divided by the 64. Okay, that value is coming into that value plus 1 adding in that. That will define the baud rate in the asynchronous communication. But whereas in case of synchronous communication, when sync bit will be 1, the baud rate is equal to crystal frequency divided by 4 into 1 plus 1. Okay, so the X value will be always mentioned, that is SBP RG register from 0 to 255. Okay, this X means varies from 0 to 255. So this is the simple operation, and it supports USART for the connection of the, as I said, that SPI I2C communication. So means whatever the previous models was considered, that can be performed connecting to the USART pin, and I can perform the communication. This is USART transmission. So if you see, it has a transmitter registers and it has a TSR, that is transmit serial register. Simply they act as a 8-bit registers. Okay, so when 8-bit will be there, 8-bit will be stored here. And when we have the 9x transmit x9 bit, means we have performed the 9th-bit communication. Okay, TX9 bit means the 9th bit will be coming at the TX9D. Okay, extra bits will be here. So how the data is coming to the USART from the port internally, from data bus is connected to the TX register, and through which data is coming here. Once this data is transmitted from the TX register to the TSR, the flag will be raised. That is, transmitted flag will be raised, TXIF. Okay, transmitted flag will be raised from the interrupt generator. The same time, this what is the data is coming, 8-bit TSR is connected to the one of the port pin of the peak control, that is RC6. Okay, so it has a transmitter and the receiver pin, and that data can be transmitted. So from the TSR 8-bit register data can be taken from the buffer controller, and that bit by bit is coming from the that RX port C, simply 6 pin. And to transmit this 8-bit data, previously mentioned, the baud rate can be defined for that from the baud rate generator. So I can have the high baud rate or the low baud rate communication can be generated. And this signal is given means what? I can make the baud rate is high or the low for the this transmit data from this pin to the other peripherals connected to this pin. This is simply USART transmitter. Okay, this is working just as I mentioned. Still, I'll repeat that part. Simply is that internally from the data bus, data is coming in the transmit register. And once this data is shifted inside the TSR, like buffer register, 8-bit from LSB to MSB, that time the flag will be raised, indicating that data is out from the transmit registers. Okay, so it is simply 8-bit data. Same data will be transmitted the baud rate defined from the SBRG. A baud rate generator will define, and this data is transmitted enabled from the transmit control register. That time this data is coming out with the high or low baud rate. Okay, if in this 8-bit only, if I need the 9-bit data, that time TX9 pin is high, indicating that this one means after 8-bit the extra signal is coming 1, that indicates the 9-bit data, and that is stored in the 9x 9D register, TX 9D register. Okay, so like this, USART will transmit the data from internal peak to the other peripherals. This is operation just mentioned here. Next is similar way, we want to receive the data from the port pin inside the peak controller, the port of USART receive. The just control register is mentioned, is shown here. Always it is coming in the first RSR, that is a receive serial registers. By checking that either it is data is 8-bit or it is greater than, by indicating this overrun bit, overrun enable bit will be there. If in that bit error is occurred, that framing error, that is indicating the this bit, framing error enabling bit, that indicate the errors or not. Okay, so once data is received in that ISR bit, this data will be shifted from that received buffer register to the serial register. Okay, so the data is I'm receiving continuously or single time is defined by the this register, receive continuously register. So this 8-bit data is received here. If 8-bit data will be there, no issue. If the 9-bit will be there, that time RX9 will be enabled and the 9-bit will be stored in the RX9D. Okay, and once the data is shifted here, the receive flag will be generated. The interrupt can be generated. Once the data is shifting from the ISR to the receive register, the interrupt signal will be generated. Same like the discuss, I can have the reception operation or the transmit operation. So only changes what? Receiver can have the single time reception or the continuous reception based on the bit that control. If you see here, we have that control register flag, CREN, continuous receive enable, and the single receive enable. Okay, that enabling that bit, I can receive the data. So this is simply operation of the USART receiver. Again, I'll repeat simply logic in that. Once from the transmitter side, data will be received. Okay, from the RC6 pin, that other port of the control data is coming here, and that will be stored in the buffer register, that is called receive serial register. Okay, if it is 8-bit data, that will transmit on inside the serial register. If it is a single time enable will be generated, only one time it is received, and the same time flag will be raised. Okay, if the incoming data, if the reception is 9th bit, so I need to RX9 pin will be enabled, and that will indicate that I have the 9-bit data, 9-bit data is stored in the RX9 bit. The same time also I can have the interrupt generation. If the data is greater than the 910 bit, the overrun bit will be set, that indicates the reception is going to be overrun. And in that, the framing error is not present or present, checked by the this bit number FERR, framing error in the receive control register. This is simply operation was discussed here. The same way it is mentioned as I mentioned here. So this is the last point of this our chapter, as I discussed. And for that sending the serial data, as I said that program is not database, just is mentioned here. Okay. So chapter number 8 also we have finished. That is I2C, SPI, USART, hospital receiver, and difference between the I2C, SPI. Three modules are there only, and we have seen that. Hope you understood this, and if you have any problem, let me know. And okay, thank you.